Okay, so we are trying to. Okay, so we will understand the projection of a vector onto another. What it is, we'll just get a visualization. So let's say we have two vectors, u and v. Okay, so and these are three-dimensional. So let me draw this for you. This is a three-dimensional plane, and this is my y-axis, this is x-axis, and this is z-axis. So in this plane, we have two vectors. Say this is my vector v, and this is u. And now, what the projection is, that we all know that is pretty basic. Say here's a light source. So it will cast an image, cast a shadow of this vector u onto vector v. My lines are not straight. I'm sorry for that. Oh, whatever. Let's focus on the concept and not on the straight lines. Okay, so what it will do is it will cast a shadow onto vector v, and this is called the projection of u on v. I'll represent it with p. It is a vector. These all are vectors, but I'll just avoid writing it. But in your notebook, you should write it. I always write it. Ah, doesn't matter. So projection of u on v is this vector p. So how do we evaluate this vector? Uh, okay, let's see. We it's obvious that this vector p has to be some scalar multiple of the vector v because they're in the same direction, right? Now, since we can see it is smaller, so k will be fractional. If it was, it can be larger, like this can be vector u, this can be vector v, and this could be the projection. Why not? This could be the projection. So in this case, if I had written v, some k times v is p, then k would have been a natural number, right? But yeah, it is pretty basic. We'll focus on this case. So, and this case. So, let me get back to the black pen, right? Now, how do we calculate what the vector p is? We will use this thing, and also we see this triangle, right? This triangle right here. It is a right angle triangle, and this is a perpendicular vector which I'll name x. And since it is perpendicular to v, I know that the dot product of x and v will be 0, right? Also, in this triangle we just made, this right angle triangle, we can say that, yeah, vector u equals vector p plus vector x. So from here we can say that vector x is vector u minus vector p, right? And now what we will do is we'll substitute this into this. So what we get is u minus p dot, yeah, it is dot v equals 0, right? 0 vector. No. My bad. This is dot product is scalar, so it will be just 0. Okay, now we know the property of dot product, we can distribute it. So this turns out to be u dot v minus p dot v equals 0, right? And it says that, okay, let me just make space. So now this gives me u dot v is equal to p dot v, right? Also, sorry for this pause. Look at this. From here, I can say that u dot v is equal to k times v dot v, right? And from here, I can conclude that k is equal to u dot v over v dot v. And we know that v dot v is nothing but the square of the norm of vector v, right? You can try this if you don't know. Just try finding the dot product of v with v. Okay, so this in turn can be written as u dot v over norm of v squared. Now look at again this black box, this thing. We were to find the projection. We were to find the projection, and which was, this projection was equal to some scalar multiple of our vector v, and this is that scalar multiple k. This is our k. So our projection will be u dot v over norm of v squared times vector v, right? So this is how we derive the formula for the projection vector. Notice that this is the projection vector. This color, okay? This is a scalar quantity. U dot v is scalar. This is the length squared. This is scalar, and this is a vector. So this is a scalar multiple of the vector v, right? And this is how we find the projection vector.